So in this next xaq-ai diary entry, you're going to see another one of my refactors, and I'm going to mention a patent that I filed on this whole loop concept. That was AI psychosis working. And that was, I think, I'm not going to call out the language model that kind of got me into that place, but I caught it, and that's why this project is still open source. But I do mention it in this video. I'll go into the process if anybody cares of how I was able to extract myself from that. But yeah, it was real. It happened. So you're going to see me apply real scientific concepts now. At least I was powering my studies. I was doing lots of iterations. So it's the beginning of me starting to manage this project in that direction. So let's check it out. Roadblocks that we were hitting in version 3, which was really trying to jump ahead and get some motion and some intelligence out of, cobbling together early pieces of the total, just really weren't working out. We made sort of a two-dimensional maze for a little bug to try to crawl around in, but we just didn't have enough topology there to learn anything. We were just hitting a lot of roadblocks. So I was like, screw it. We got to build this thing from the ground up. We need to have this cellular bath where all of the components can just live in C++ world, connect to each other, have complete configuration, and all of the components from the original design, which is part of the patent, but also, after doing some more research with Claude and just more Google searching, more thinking about the whole thing, we were missing some key components, mostly, the neuromodulators actually feeding back down to the EPMs, right? So we need feed forward and feedback at the same time, like that full circular pathway for all of the modules, so that as sensor data comes in, it feeds forward through all the different parts, creates knowledge graphs through all of the modules, and finally we get to the final lateral voter, which creates the growing neural gas. That's creating the knowledge of the world, right? And then that's going into the action encoder. And things that were missing from the action encoder were actual sequences, right? So the only way to actually build movement that makes sense, instead of just being per tick, like fire, go left for one tick because of this one thing that happened, like the history is gone, basically, right? So we need to actually compose sequences of movements and then fire those off when a certain part of the knowledge graph happens, right? This is all very, biologically sound stuff. Plus, really convincing Claude not to start hand tuning things and instead make every single parameter dynamic. So when you start this engine, start the brain, it's learning from scratch every single time, and it doesn't have to be hand tuned. And you turn it on. If that configuration of the brain works, it works. So right now we've got the Agma cell, which is basically just a room. And if I run it, we can see first person view of the agent. And what we've got going on here is, here, if I push V, we can see the top down view. So we got our little guy. He's got 6 whiskers, and he's got flippers. So basically it's got some spiking. I wanted to go back to the spiking neural networks for the actual motor skills, because that works so well in my early experiment with spiking neural networks. It just seems very organic and much easier for this type of thing to fire off rather than like floating point values for turning. Like that's just not really a motor skill, like one of the things that did kind of pop out early on was when you have something that's too blank, like even this room is too blank, right? Or even if the topology of the organism's body is too simple, this thing has a hard time learning. You need the complexity to pull patterns out of. If you have just basically blank nothing, there's nothing to pull patterns from, including your own dynamics. So you actually need to have a more dynamic creature in order to pull more useful information out of it, in order to build a pattern of the world, right? So this guy, he does have a tendency to turn right, which is kind of annoying. But just to look at the environment here, if I can basically use the number keys and build bigger rooms. So this is level 2, level 3 is basically the hardest mode. I can turn on pillars, right? So we can put some obstacles up. We can also turn on terrain, which gives them some more rough, slightly raised surfaces. That was to kind of tickle the the motor EPMs a little bit more. I'm not sure how effective that is. We still have this tendency to turn right? However, he's getting close to food. I don't think he has enough brains yet to find it. So it looks like he did get an eat early on, which is not good once he's in the more advanced realms, we'll say, right? Because now he did learn something, but that was actually a little bit too easy. So one thing I have noticed at about, he's going to find it. That's really good. So usually it takes about 5 minutes for this guy to find food in the hard mode. He just happened to find it. You can see he still has kind of this circular pattern that'll develop in easy mode. I got to figure out why he just wants to go around to the right. That means something's not quite balanced. You would imagine that if things were perfectly random in his brain, he would go left and right and all over the place. But why does he turn right? So one thing I did notice, like after this thing's been going for a while, he'll start to hang out near the food. That's one thing that's really interesting. And we'll take a look at his brain in a second. But even in the hardest mode, there's really like the only thing this little guy can experience right now and build patterns off of is the actual environment. So he's doing that. He's not getting stuck anymore. That's really good. And I'll show you a few ways, a few of the modules that keep him from getting unstuck. But it hasn't been quite long enough for him to like realize like, hey, here is where the food is. But he will. The little guy will start to hang out in this area and just like gobble up the food because the food keeps appearing in the same place. So he is learning that type of thing. But right now he's still kind of random. He's walking around in circles. So while he's doing that, while he's learning his environment, let's go to the brain here. So this looks really complicated. Right now this is not editable. It's using Godot's, basically it's, if I can actually expand it. I can, yeah. So this is using Godot's node-based editor, but it's not. This is not for programming. This is just showing you what the cellular bath looks like, and we can see all the different components that we build that are running in real time. And I can actually show you something that's very fascinating as far as the CPU usage. So we're actually running several instances of Godot right now. It looks like these are just hung processes from before, but we'll kill those later. But you can see right now with it, the one that's running the actual simulation that we're looking at is using about 3% CPU. On the, these are my, I guess we'll call them statistical runs right now. So this is the flat hierarchy without all of the modules that you see here, slightly less complicated. I'll explain what that is. And this is the hierarchical one, which is what's running right now. It uses a little bit more CPU, but like the fan's not even running on this computer. Like it's barely doing anything. A lot more is happening because of the Godot engine than it is for the actual brain itself. And I'll show you why. So right now, these are the inputs, basically the sources. We want to think of sources on the left and sinks on the right. We've got the IMU, which is the basically your inertial, I forget what IMU means. Yeah, so it's sort of what you would use for navigation, right? So basically, we've got kinematics, right? Your acceleration, you're moving left and right, that type of thing. We've got our whisker inputs here. We've got left, right, 6 channels of whiskers. We've got energy, how much energy that can passively drain. We've got your sense. So it's got nostrils. Basically trying to find out like, hey, is there food nearby? And basically the terrain, like, is it rough? Is it sloping? There's no camera connected yet, right? So this thing can't even see. All I can do is smell and feel, and it is aware of its body. Now, Yeah, I always want to rush ahead and gives this thing more senses. Like, oh, I bet it could, I personally want to rush forward and give it more of a body in order to navigate its world. What if we give it the camera? What if we do this? But no, we've got to stay. We've got to just add one thing at a time and be really careful to make sure that the one thing that I'm adding actually makes sense. So let's look at the next layer up. So these are all the EPMs, right? So we already know what EPMs are from versions 1 and 2. That was our first nugget of, of our atomic unit of this whole brain, right? So the EPM is our epistemic predictive memory module. And so the sensor modality goes in. For example, we've got all 6 of our whiskers are represented here. We've got our terrain feeds into here. Remember, it goes in, it gets encoded geometrically, it gets put into a graph, the growing neural gas, and then it outputs a reality token, right? And we can see how the reality tokens are wired here. So if I turn off all of the other connections, remember, this is all pub sub, not a public sub that you can eat, a publish subscribe system. Right, so all these other modules are subscribing to the outputs of other modules, right? So all the EPMs subscribe to the outputs of, for example, the IMU. Interestingly, the IMU, yeah, so this is actually the whole, the IMU is actually your proprioception. That's your body awareness. That's going into the whisker. I think that's what's actually giving us the whisker source, right? So this is actually from the game engine, right? So these are inputs from the game engine. Keep in mind that we are not giving it anything about its position, anything about, where it is in the map or anything like that. This is really just about, the inputs that would represent senses inside of that environment, right? We're being very strict about that kind of thing. So here we go. Whisker EPMs are subscribing to whisker channels, terrain subscribing to the terrain channels, ascent is subscribing to ascent, IMU is acceleration, stuff like that, right? That makes sense. So what we did with the hierarchical, right, as opposed to flat, so right now you can see I'm running my hierarchical sets here, so hierarchy did help, right? So if you can see over here, I'm jumping around, but who cares? So in the flat arrangement, a flat arranged brain has the same number of EPMs, but they all feed one lateral voter, right? And the problem with that, well, it's not a problem. If you've got like the problem, the problem is that when you have more and more senses, one lateral vote is not enough to denoise all of that information coming in, right? Our brain doesn't work like that, and it doesn't necessarily work for this either. You can see the number of hits that are possible, here with the flat arrangement, and as soon as we bump it up to a hierarchical arrangement, basically just adding one extra lateral voter, right? And what that lateral voter is doing is basically giving a consensus between the IMU and the terrain. That's all it did, right? Let me see, is anything else wired up to this? No. Only one extra lateral voter denoised the terrain from the IMU, and you can see the hits that are possible now. So it went from maybe averaging like 7 hits per 5 minutes to quite a few more. We got 13, 17, 37, 19. It's still possible for it to just have one, right? It gets stuck in a corner for 5 minutes and now it's dead. But, think of these as like populations, right? These are deterministic seeds, so we can have repeatability. Looks like seed number 45, it doesn't do great with, but on the flat one, it did. Well, at least it got 4. But either way, seed number 45 is hard. It's probably because there's a couple of, it's getting stuck in a corner or something like that. Or this could also have the pillars in there. I'm not exactly sure, but it's very easy for it to get stuck between 2 pillars and kind of just go around in circles, mostly because it has that circular behavior. But that's okay. We're still learning a lot. We need to get these kind of like statistical baselines before we make the brain more complicated, so we know whether we're going forward or backwards. But basically just adding one extra voter along with the terrain EPM, really denoised the IMU and the terrain, right? So this lateral voter feeds this lateral voter. I probably should move these things a little bit out of the way so we can see the actual order, right? So this is like subvoting, right? One other thing that we want to try is like, what if I took all the whiskers, or all the left whiskers and all the right whiskers, lateral vote those, and then send it to voter number 0, right? Voter 0 is the top level. That's its consciousness, right? Kind of. We're definitely not there yet. But basically, like, that is the fractal design that I was always thinking of, is like, okay, you've got a bunch of EPMs, you put them together, they lateral vote, and then either they feed another EPM, right? So now you've got a growing neural gas of the consensus, right? Which isn't computationally expensive, right? Remember, as you everything just scales linear, because we're not doing any like matrix multiplications. Everything's just geometry and signal processing. So those are things I want to try. I want to be able to click these brains together. We're going to add some, the ways of actually like changing the connections. Right now, everything's just like, this is read only, right? This is all, it's pre-baked inside of the JSON. Now we get to look at it, right? Move it around, kind of see what's happening. But either way, after that, after we take out the reality tokens, if we want to look at consensus, right? So all the consensus, so obviously the consensus voter, the consensus coming out of the lateral voter. See, look, this is interesting. Oh, I know why. So consensus is different than reality tokens. So the reality tokens are all connected. The consensus tokens are different, but I would think the consensus would want to go to the lateral voter. I have to see whether that's a bug or if it's actually just not connected properly. That's why I want to actually connect these things manually and try stuff out and just screw around with it. Not quite there yet. Got to build that architecture. I want to mess around with adding a lot more of these lateral voters and just like see what happens when you grow it horizontally or vertically, or depth or width, right? Lots of fun things to try. Motor repertoire was another thing that we had to add. This is the thing that stores the chunks of movement, right? So we have 3 chunks that have been developed. The homeostatic drive, basically novelty, satiation, energy, scent. That's coming out of here. I guess we can say it looks like that's wired up for action, prediction. Oh, that's other, right? So that's part of the action decoder. Yeah, I've got to experiment with these parts more. Since Claude invented some of them, I'm like, is that how that works? I'm not entirely sure, but but yeah, we gotta write the user manual so it's easier to build new brains. But yeah, that's the whole thing. This is going to be super fun once we have more complex organisms, to actually build an organism, hook it up to the system, build a brain, see if you can get it to scale. Yeah, it's going to be really cool. You can see action does feed the motor. Those are the 2 flippers on either side. We've got events, hits, reward. Basically, if you hit the wall, ouch, right? That hits the neurochemical. So part of this, just to stay inside of the spirit of embodied intelligence, is the things that we actually have to build are the body and the world, right? The body hasn't gone through evolution, right? It might later, but not now. For now, we just have to come up with a solid enough analog of an organism, an agent that can exist inside of an environment. Originally, we were trying to have it play video games, but that's, I quickly realized that this thing has to be first person, right? It has to have its own perspective inside of an environment. So the kinds of skills that we need this thing to have must be very closely tied to something living in an environment, not like a person trying to play Pong. Pong is a very it makes sense to a person because it's mimicking us playing tennis or whatever, pickleball. Or breakout is like, okay, I'm moving my arm, I'm bouncing a ball. There's like a lot of cognitive things happening in my brain that makes Pong make sense, right? But if the agent is just a paddle that moves around inside of a blank world, and it doesn't have enough there for it to actually chew on. We actually had to make a world for our organism and have it exist inside of it. And now we can add things like health, and we can start experimenting with evolutionary algorithms, competing for food, all kinds of really fun biological experiments using this kind of experimental framework, right? That's what we're trying to do. We're trying to build this thing up from the beginning, and so it can scale and scale and scale and make more and more complex and intelligent agents that learn, don't forget, and have all of the continuous embodied intelligence and active inference. So yeah, it's working. Let's take a look at our guy now that he's been running for a while. He is hanging out in the bottom left. He's had 13 eats. That's actually pretty good. So look, he is somehow learned to hang out in the bottom right corner, right? He has all of this whole map to deal with, right? So he's probably spends a lot of time stuck in that one corner, but he's consistently eating now, right? Technically we could look at his brain and try to, maybe reverse engineer what's happening here. It's already pretty complicated. It looks like spaghetti, but guess what? If you ever look at cellular life, it's a mess. I'll have to think of better ways of like visualizing this. For now, it's just like, seeing how these things are connected, published and subscribed to each other. So yeah, the guy's hanging out here at the bottom right. I don't know if it's because he knows this is food or something like that. One thing I can do is add more pillars. We can see how he navigates those. But for whatever reason, like he could easily have been hanging out in this corner the whole time, right? Let's see how he behaves now that I changed his environment slightly. If he gets unstuck, is he going to be able to find his way back? Because, well, actually, look at this. This is fascinating because, while he found his way to that food and just hung out in the corner and kept eating the food. Now, as soon as I changed the environment, it's like, does this little guy have like some kind of ability to navigate these pillars and now he's lost? I don't know. We didn't bake anything into this, right? And one of the things that we probably should do is give a little bit more of a stronger rewards. Like, hey, like what would happen in a cell, that has a less so this is like planaria level multicellular organism style brain, right? With a couple of neurons, biological neurons, not artificial neurons, right? What that's a real neuron has quite a bit of agency, right? It started off as a fully fleshed organism with agency, so we have to think about how what's possible with like real cells. It looks like this guy is having to relearn his environment. I can't say for sure. That would be another test to run, multiple iterations with multiple different seeds. Can they start to find their environment, start to learn it, start to eat more and more often? So I'm just going to let this one run, see if he starts to hang out in the corner again and just eat more, or is he going to stay lost? I don't know. Do we have enough forgetting in there? Is he able to kind of override and lose any bad memories? And make up for this new environment that he's in? I don't know. One thing I do know is that, I would want to spend more time on the actual body itself. It's like, this isn't this isn't a bug that would necessarily be able to survive, right? Like, this is a hand-built organism where I think a really interesting just exploration and creation of life experiment would be many generations of these types of bugs, allowing the brain to grow organically and evolve along with the body, right? So, how sensitive are, like what about the bilateral, like physical parts of it having some evolutionary traits as well, right? And we'll really have to, draw on the latest research, that has been showing, especially in computer science, that evolution is not random, right? It's exploring the combinatorial space of its environment, right? And how do we code that into this kind of system? I think it's possible. I gotta like do one thing at a time. We're not quite ready for that yet. So yeah, we'll see how this guy does. He ate 15, but ever since I added more pillars, he got lost. So we just have to see, like, is he able to relearn? Do we have to, make it so that he can forget easier? Oh, he found one. Let's see if he holds on to it, right? Keep in mind, his entire nervous system has knowledge graphs of this space, right? It's just a matter of like, are the old ones causing issues? Is he able to prioritize? Yeah, we'll just have to see. So I don't know. I'm just going to let it run for a little while. Yeah, because I am kind of curious. But I guess, yeah, the next couple things I do want to try. The next step is a couple different games, right? So other games, the cart pole, where we're trying to balance a pole on the cart, keep that up and moving up and down. We want to actually use benchmarks that for active inference that have been used before. There's an official quadruped model that's been used. That's going to be really fun. Actually having something like this learn how to walk and develop its own gait and get around. One thing I really want to do though, like part of the fine tuning of the body part, which is going to be super important. See, why is he doing up there? What are you doing? Why are you in the top right? That makes no sense. I don't know. Anyways, yeah, see, one of the things that's really interesting, he's got one or two motor chunks that he's developed to he'll grow a new motor chunk when he finds food, because that has a very cementing part of his behavior. That's one thing that we are hand building, right? We can control this organism. The only way we're allowed to control the organism is how we connect the inputs and the outputs, right? We can connect the inputs via whiskers, whiskers, scent, all those things, where that's allowed. But we are skipping evolution. So evolution would never have allowed this guy he would have died a long time ago, right? So any type of tunable parameters that he could pass down would, go into those turn right somehow, wiring it up. So like if you go past the food and you brush it with your whiskers, turn right and get it, right? Stop the flippers on that side so you spin around and get your food. But we can't program that. We're not allowed to put in any if then, nothing like that. The system has to figure it out. And it's quite clear, by looking at a brain that's already this complicated, that, the ability to rewire this and have it be elastic is super important. And, there's ways of doing that that's on the roadmap for it to add new EPMs, and the next generation might magically or randomly, I don't know. One thing I want to do, maybe with an LLM or basically, maybe take some cues from AlphaZero and call this a game, right? You've got these components. How do you connect them together in a way that this guy is more effective in the world? And is there a way of speeding up the process of evolution? Or does evolution just have to take a long time and be super annoyingly slow? I think by building environments that can run faster, probably the thing to do would be to run these agents in, very, obviously headless, but one environment with thousands of agents, I think would be much more computationally efficient than multiple instances of Godot running at the same time. I think that was kind of causing some issues before when we're trying to run a bunch of them in parallel. It doesn't use a lot of CPU at all, but just running the Godot engine takes like 100 megabytes. So, that's, just something that happens. So, this guy is unfortunately just sort of circling the middle of the board. It's got that tendency to turn right. But you know what? Yeah. Evolution will make the ones that turn left eat more, and they'll survive. Right? It'll be really fun to have a bunch of little quadrupeds. If those guys get to work, one thing I want to experiment with that'll just be fun is, the sort of transferring of DNA. So obviously this has a lot to do with the DNA, the inputs and how they're wired up this is all part of his cellular or the organism's makeup. And those things can definitely be passed along, snippets of it. It just, randomly just grabs some part of the JSON, sticks it in the other one. That would be interesting, right? Just if it bumps into it, they have a fight. One tries to eat the other one. Yeah, that would be really fun. These guys, not only are these green dots food, they are also food to each other. That's how it's got to be. That'll be fun to watch. And that because putting those kinds of drivers into a system like that will make it evolve faster, right? Like we need to have that kind of thing. We need to be able to build like these kinds of virtual environments to bootstrap these patterns, and then we're going to start seeing patterns emerge inside of this. Like, it works really well when you've got a complex sensor modality. For example, if I got one camera, but I've got dorsal, ventral, salience, optical flow, all those different types of encodings, all coming in, maybe in pairs or, into pairs of lateral votors or several different layers, right? So we know our optical system goes through several different layers before it even gets to the visual cortex, right? And then it explodes from there. So all these things connected together to make really good vision work inside of certain kinds of environments. So yeah, that's where this thing's going. Really want to build a bee, something that can fly around and be a bug, to something that can be an ant. Like that would be huge, right? And it learns completely on its own. And the only thing that we built was the body. So that's where we are as of May 1st, 2026. Cheers.